In the first lectures, I discussed I gave you a picture of energy flow picture of particle physics, and what I'm going to do now is to explain some recent progress in understanding the structure of the general structure of our G flows in four-dimensional quantum field theories. Okay, this progress may not be of immediate direct relevance to the search for the new theory, for the search for the fundamental theory of particle physics, or for the more fundamental theory of particle physics, but perhaps it will, okay? And it certainly rules out some possibilities without doing any experiment, under some assumptions, of course. Okay, so the two subjects I will discuss are the A theorem that establishes the irreversibility of the renormalization group flow, namely that you cannot go through the same conformal theory during the flow. Well, you cannot go through, one way to say it is that you cannot go through the same point in the flow twice. It's not quite that, but it basically states that when you have two conformal theories and one flows to the other, the opposite cannot happen. Okay, if you flow from one point to one, you cannot flow back. And the second result is instead a result which rules out, under some assumptions, which are mostly technical in my view, non-standard asymptotics in quantum field theory. And let me tell you what I mean by the asymptotics in quantum field theory, just to give you an idea. So, of course, here in this part, I will basically derive theorems. So, for that purpose, I will work in a more idealized situation rather than in a general effective field theory. I will, in a sense, I will consider quantum field theory that are truly completely well defined in the sense that they have a UV limit. Quantum field theory that, in a sense, can flow in the far UV to a conformal theory, so they can be completely defined, like for instance, Young-Mills. So imagine you have one such theory, and you start from the UV, perhaps from a UV fixed point, and then you flow towards the infrared. And the question is, what can happen? Okay, so let me show you three examples of what can happen. It can happen that the theory flowing from the UV, it will flow to a new fixed point in the infrared. Okay, it can happen that starting from the UV, it will start going around at a certain point, and it will get some limit cycle, and will spiral along this point forever. Okay, so the end result of the evolution could be a limit cycle, or you could have weird behavior like ergodic strange attractors, in the sense that it could spread around without any rational. A trivial example of this, but this is trivial if you have two limit cycles that are not rationally related, but that's a simple case. Okay, in spite of this possibility, and on top of that, it could be that this fixed point that you reach in the infrared, it may be purely scale invariant, or it may be scale invariant and conformal invariant. Okay. Now, in condensed matter, examples of this variety exist. In particular, cycles exist, the so-called Efimov cycles. In non-relativistic theories, examples like these are known. And on the other hand, in relativistic unitary quantum field theories, the only examples we have been finding through the years is CFT asymptotics. In all the examples we know, the asymptotics is a CFT. Or if you want, it's either a CFT or the empty theory. Okay, if you give a mass to all the particles, the far infrared is the empty theory. Now, the empty theory is the simplest conformal theory. If you want, it has all the symmetries. There's nothing. Okay, but in all the other cases, okay, the theory is conformal. Let me give you an example. Take, for instance, QED. QED and trivially so if you want, often trivially so. In QED, what you have electrons and photons. You reach the electron mass. Below the electron mass, the photon becomes free. Okay, there are still interactions that are suppressed by the inverse mass of the electron that are associated with, for instance, these diagrams. That go like 1 over m electron to the fourth, f mu nu to the fourth square plus other contractions, okay? And f mu nu tilde square, okay? There's also, well, okay. And these are the oil and higher orders, okay? Higher orders in the 1 over mass of electron expansion. So from the point of view of the infrared theory of QED, okay, what you have, QED, is just a free photon plus sum of operators suppressed by inverse powers of the electron mass, okay, inverse positive powers of the electron mass. So it looks like one of the effective theories we have been talking about, but the only thing is that because of the many indices and because of gauge invariance, the only interaction you can write are irrelevant. They are operators of dimension higher than actually higher or equal than 8. The leading interaction starts at dimension 8 and is given by this. Okay, so however, in the very far infrared, these terms are negligible, and what you flow to is free Maxwell theory, which satisfies conformal symmetry. Okay, it's a conformal invariant. It's just a special case of a ordinary free four-dimensional field theory. The same happens in QCD. In QCD, in massless QCD, if you turn off the quark masses, and let's say you also turn off the electromagnetic coupling, then the low energy, the general limit of QCD is just massless pions. In the far infrared pions, the leading term is just the pion kinetic term plus interactions that have the form of a sigma model. They involve 1 over f pi, and there are they start at dimension 6 and involve 4 pions and 2 derivatives. Okay, the pion is a Goldstone boson, so whenever it couples, there must be a derivative. It cannot have a potential in the limit where there are no quark masses and alpha electromagnetic is equal to 0. Okay, this is m quark equal to 0 and alpha electromagnetic equal to 0. So again, plus higher orders. Okay. So you're again in the situation we depicted in the first lectures. Free field theory, no relevant, no marginal operators, and only relevant. In principle, you could write the reason why you don't have any mass, any quartic without derivatives is the shift symmetry of the Goldstone field. Okay, this is a Goldstone boson, cannot have any interaction which does not involve derivatives. And again, so what is left when you go to low sufficiently low energy is just a free scalar. That's a conformal theory. Of course, this is trivial. There are more interesting examples, although these are not found in nature. In the case of supersymmetry, as I already mentioned, there are examples where when you flow to a new fixed point, and the new fixed point has been understood and shown in all the cases where one could show it to be conformal invariant. Or otherwise, you can have trivial cases. Okay, trivial case is QCD with mass. Everything has a mass. Everything is gapped. The infrared theory is the empty theory. So in particular, as I said, there are no known scale invariant theories without conformal invariant. These are known in jargon. Why is this not going away? No, sorry. Okay, like this. Okay. Okay, so in particular, there are no examples of theories which have scale invariance and not conformal invariance. I told you previously, and I partially explained this in one of the questions yesterday. What is the deal? So theories that have scale invariance and not conformal invariance are endowed with a conserved scale current of the following form, where V is a current that is not conserved, and it's not equal to itself the divergence of another current. Okay, if that is the case, then you have a genuine theories which are scale invariance and not conformal invariance. Now it is known, as I mentioned, and this is a paper that was shown this is something that was shown long ago, that in all, just by inspection, all four-dimensional quantum field theories that do not involve dimensionful parameters, four-dimensional theories that have only Yukawas and gauge couplings, that are scale invariant, are also conformal invariant. This is just by inspection. Okay, so if we want to build a scale invariant and not conformal invariant theory, necessarily we have to use quantum effects. We have no example at the classical level. So this is making things more complicated and harder to figure out. Okay, you don't have a classical example. So this is, you genuinely have to work to find a quantum example. You cannot have a classical example in 4 dimensions. And as I said yesterday, there are some arguments that tell you that this is there's at least one argument that tells you that this is suspicious, although is not conclusive, and is the following. These are conserved current. This is conserved. This is conserved. This is not conserved. Okay, but conserved currents are known, it's just a theorem of quantum field theory, not to have an anomalous dimension. So given that V is the difference, if I bring T on the other side, is the difference of combination of conserved current, so say operators, composite operators that do not have an anomalous dimension, to all orders in perturbation theory, then V itself will not have an anomalous dimension, which means that V is a non-conserved symmetry and a non-conserved current without anomalous dimension. And that's very, very surprising, because whenever you have a non-conserved current, it receives an anomalous dimension. Okay, it has no protection. It's just a fact. Although it doesn't tell you that it cannot happen. Okay, it just tells you that it seems strange. And in many cases, there is no candidate for such a symmetry. Okay, so for instance, in QCD-like theories, the only candidate for the current V, which is known in jargon as the virial current, the only candidate for V must be a current which is a singlet of all flavor symmetries, because it has to mix with singlets like the energy momentum tensor. It must be a singlet of all flavor currents, and it must not be conserved. So the only current we have at hand in a QCD-like theory of this type is the axial current. But the axial current is parity, as the parity transformation properties that do not match the parity transformation property of T times X. That's one is an axial vector, that is a polar vector, and therefore it cannot mix. And because of that, you can simply say that in QCD-like theories, there's no, and in particular in supersymmetric QCD-like theories, there's no candidate, there's not even a candidate for this current. So this is why these theories can be shown to be conformal invariant in a sense. Okay, so there's not even a candidate for this current. However, in other cases, in general, we don't know. Okay. Now you may think that this is academic, but I think it isn't. Okay, you may ask yourself, well, as we said, whenever there is a separation of scales, as I said, the theory in the between is approximately scale invariant. Now, if there is a separation of scale between the standard model and whatever new domain of physics exists in the UV, maybe gravity, maybe anything you want, then it's a fair question to ask what are the possibilities. One question is it possible that the theory that the approximate fixed point that describes the standard model in the far UV is scale invariant, approximately scale invariant, but not conformal invariant, perhaps strongly coupled scale invariant, but not conformal invariant? That's a fair question about what is possible in particle physics, right? So it's worth knowing. It's not buying you any money, but I think it's worth knowing. And it doesn't require experiments. So, and we probably never do experiments that extrapolate the standard model. So we do thought experiments, or we try to use ingenuity. Okay, and it turns out we can say things. Okay, let me now start with the more technical discussion. So I want to discuss the investigate the properties of RG flows. So the RG flow, the process so what is the RG flow? The RG flow describes, as you've seen, how the dynamics changes when I change the energy of my process. And or you can view it equivalently. You can think of it as a change of the action. Okay, the change of the dynamics can be encoded by the change of the action under a dilation. Okay, as you have seen, when yesterday there is the dilatation current, okay, which is equal to T mu mu, okay, the trace of the energy momentum tensor. Let's say in a case where let's consider the simple case where you are close to a conformal fixed point. This trace of T mu mu is known in quantum field theory to be written in terms of a sum of beta function times operators. Okay, so the amount of violation of scaling, which is, if you want, the divergence of the dilatation current, is controlled by the beta function. Okay, so the RG flow parameters, the beta function, control how the system changes under a dilation. Okay, so studying the flow amounts to studying how the Lagrangian, or if you want, the quantum effective action, transform under a dilation. So I want to use dilation as a symmetry and derive generalized selection rules for dilations. Of course, general selection rules for dilation per se are perhaps not so interesting, because if dilation is a rigid dilation, it's just dimensional analysis. So we want to get more out of it. So what we do, we want to do local dilations, okay? And if we do local dilations, then in order to describe how the Lagrangian changes, we also have to promote the fields and the coupling often to fields, okay? So we will apply a few games, okay? What we'll do, we will formally restore the dilation invariance by promoting all the couplings to fields. And in some cases, if the dilation symmetry is promoted to a local symmetry, we will have to gauge it by adding the suitable gauge field. Okay, so we'll play in two related games. One game is to take the theory in flat space, okay, where you have a metric and couplings. These are games, okay? I'm not saying that it is necessary to use this to derive the results. It's just that the remarks that follow from all this technique encode the information in an efficient way. One could derive the same result that I will get at the end without ever talking about sources and spurions and fields promoted to sources. Could derive them just by studying the properties of correlators of operators and applying word identities. But that language would be far less intuitive, and I think this is going to be quicker. Okay. In fact, all these theorems have been proven precisely using this viewpoint, and the alternative viewpoint apparently did not give anything. Okay, although it could have. Now, so the idea is to promote the metric and the couplings to fields. In which case I will be able to promote the dilatation symmetry to a local symmetry, called Weil symmetry. Okay, the Weil symmetry is the local version of dilatations. Another game I will play is to keep the couplings constant and turn on a metric, a conformally flat metric, a generally conformally flat metric. Okay, I just take my quantum field theory and I put it in a space with a metric, which is just eta mu nu times a field. Okay, so this field, given that it controls the length scale at any given point, is a scalar field. Okay, and it's called the dilaton. Okay, this dilaton field is not a physical field; it's just an external field. Okay, what I'm doing here is not much different than what you do when you do QCD. Okay, and you study photon interaction mediated by QCD. Okay, you treat the external photon as, given that it's weakly coupled, as an external field, classical field, and then you consider quantum effects coming from QCD, from hadrons. Okay, from strong dynamics. Sorry. Did you say? That's a function of space. I'll write it either this way or this way. So these are the. I'm very poor notation. It will be shown in 3 different notations, but it's always the same field. Is that the question? It's a function of space-time. Space-time, not space. Space-time. Sorry, space-time. So okay, these are the two incarnations of dilatation in flat space, dilations, okay, and conformal transformation that you saw the other day. Now, when you go to curve space, okay, when you turn on a metric, you can upgrade these symmetries to a symmetry known as Weil symmetry. Okay, so you can, in other words, when you go to a curve space, you can view. You can picture this symmetry as arising as subgroups of the group of diffeomorphisms. They're just symmetry that are embedded in so D and K mu are contained into the group of diffeomorphisms times Weil symmetry. And Weil symmetry is given by this transformation here. Okay, Weil symmetry is a symmetry under which the metric is simply rescaled locally. Okay, and the fields are accordingly rescaled locally with a weight which depends on the type of field. Okay, so for instance, for scalars, K is 1, fermions is 3/2, and so on. Okay, vectors is 0. Okay. So the Weil weight depends on the type of field you're looking at. And now it's a little exercise. It's an exercise that you can do if you want to check that what I just said, that there is a subgroup of Weil transformations. So this transformation acting on the metric and diffeomorphism transformations of the metric. Okay, that leaves eta mu nu invariant. That leaves the flat metric invariant. And the subgroup is precisely the conformal group, okay? The conformal group in 4 dimensions, the group of Lorentz plus dilation plus conformal transformations. Now, because of that, if you have, it's just a simple result, if you have a Lagrangian or an action that is invariant under both diffeomorphisms and Weil, okay, if this Lagrangian which has the whole symmetry, okay, when you take this Lagrangian over flat space, okay, G equal eta, this Lagrangian will be automatically conformal invariant, because conformal transformation are the subgroup of the general group of symmetry of this Lagrangian that leaves eta invariant. So it leaves invariant your fields. Okay, so so it will set the just by changing phi. Okay, the resultant transformation of phi will be sufficient to keep the Lagrangian invariant. So Weil invariance and diff invariance imply conformal invariance. The converse is also true, at least at the classical level, and you can check it by inspection, at least in all the cases where you can check it. So the notion, the basic statement here is that the notion of conformal symmetry gets upgraded in curve space to the notion of Weil symmetry plus diff invariance. Let me give you an example of this. You already saw my discussion of the free scalar field. That's a theory that is certainly scale invariant. I investigated the issue of conformal invariance. In particular, I looked at the trace of T mu mu. Trace of T mu mu is not 0, so the theory doesn't look directly conformal invariant. However, you can define an improvement of T mu nu in the following way. The term you add here is automatically conserved. You can check. It's totally. This is a transverse projector. Okay, so when you act with mu on it, you get 0. So this is automatically conserved regardless of the equations of motion, and you can check that the newly defined energy momentum tensor is traceless. So this proves that this theory can be made, is scale invariant, is conformal invariant. And I had associated this improvement term to the possibility of adding to the ordinary action of flat space a term which involves the Ricci scalar, okay? And in particular, this 1/6 corresponds to this 1/6 here. Now, it turns out that this Lagrangian, so this Lagrangian is what you have to do to couple a scalar field to a metric in such a way that the energy momentum tensor that follows from it is automatically traceless. So this guarantees that the definition of T mu nu manifestly displays conformal invariance. But also, the resulting Lagrangian is automatically Weil invariant. In particular, you can check that if you do this transformation, if you rescale phi in the following way and the metric that way, this is kept the same. And in particular, you can choose phi, you can choose sigma to be equal, you can choose e to the sigma equal 1 over phi, okay? E to the sigma equal 1 over phi. That sends phi into 1 and the metric into phi square g mu nu. Okay, this is a symmetry. Okay, using this transformation, you can set you can package together in a whole Ricci term both the metric and the scalar. Okay. Now notice in this situation, now here I'm playing the game. So this is all formal. Okay, if throughout all the discussion the metric will be a formal external field, classical field, I will never do path integral on the metric. So I don't treat the metric as a truly fluctuating field. It's just a trick. It's just an external field that I use to make manifest the symmetry of my theory. Okay. So in particular, if I want to compute so the correlators of the T mu nu, the energy momentum tensor, will be obtained by deriving the quantum effective action in the total metric with respect to the metric itself, and invariance and the diffeomorphisms with respect to the change of the external metric will allow me to derive the standard word identity of the energy momentum tensor. So it's purely a technique. But notice that if the metric were dynamical in this case, okay, the metric would be able to swallow this field, and the field disappears. Okay, in the newly redefined Lagrangian, you just have the metric. This is just telling you that this is a gauge symmetry. Okay, this is again, it's a redundancy. Okay, a Lagrangian for a scalar and a metric which is endowed with this symmetry truly does not have the scalar. Okay, you can write it this way, and the scalar is not visible. But this is not the game we're going to play. Well, the Weil term is conformal invariant. The R square is not conformal invariant. It's scale invariant, but not conformal invariant. The Weil term is. Okay, now again at the classical level. So if you have a Lagrangian that is invariant under Weil transformation, let me go back to Weil transformation here. If you have now a Lagrangian that is invariant under Weil transformations, okay, in an external metric. Let me show you how you derive that previous result. So you have a Lagrangian which is invariant under Weil transformation. So the action, so this is the Weil transformation of the action. This is the change in the metric. This is the change in the fields. If the action is invariant, this is 0. Okay. Now, and this is 0 for arbitrary sigma. Okay, that's a local symmetry. Now imagine you are on shell for the ordinary genuine dynamical fields. Then this is 0, just the equations of motion, and what this equation amounts to is simply that the variation of the action with respect to the metric contracted with the metric is 0, but the variation of the action with respect to the metric is just T mu nu. So this is simply telling you that T mu nu is 0. This is how you derive, using Weil symmetry, the property of the energy momentum tensor. So a conformal invariant theory is upgraded to a Weil invariant theory in an external metric. And what are the properties of the energy tensor of this theory? You derive it simply from this equation, okay? And the property is that T mu on shell S is 0. So this is what we already knew, but this is another way to view it. And notice that this follows locally because we were doing a local Weyl transformation. Imagine that for some reason our Lagrangian only had global Weyl symmetry, okay? Rather than local, only global. That is to say, it has a symmetry, but only for constant sigma, okay? In that case, here we need to keep the integral, okay? So this is an integral over a constant, okay? Again, on shell, this drops. And what we have now is not the T mu is 0, but the T mu, the integral T mu is 0, okay? And the integral T mu on shell is 0. That means that on shell, T mu is a total derivative. And again, this is the same result we already obtained before, a scale invariant theory, globally scale invariant without conformal invariance, as the property of having an energy-Johansson tensor, which is a total derivative. Okay, so you see the two differences. Scale invariance amounts to global rescalings in an external metric. Okay, global, and conformal invariance amounts to local rescalings. So these are the two different. But we already saw it before, right? Scale invariance is just a global transformation of coordinates, while conformal invariance, which was a special transformation of the coordinates, where the geometry was dilated in a different way in different points. Okay, now I want to come to the main discussion. Okay, and so what I want to do is to take my theory. Okay, my theory defined by a certain path integral, and put the theory in an external metric. Okay, some metric. Okay, may even want a metric which is asymptotically flat, but it could even be various games have been played. Okay, but let's keep it general. Okay, now when you do that, of course, as you know very well, you have to define the quantum effective action, which is your path integral, your partition function. Generically, I mean, normally, in fact, in all cases, to define such an object, you need to regulate and renormalize your path integral. I'm assuming that this can be done keeping diffeomorphism invariance. There is in the paper we wrote, there is even some comments on how you can control the same results, even in cases where you have gravitational anomalies. Okay, but this is mixed gravitational anomalies between gauge and gravity, but there's no need to insist on that. And I don't like those theories. Okay, let's assume the theory can be made diff invariance at the quantum level. Okay, where it is in quantum field theories that have a chance of making sense, right? So. And again, it's regulated and is made finite by renormalization, by adding the suitable counter terms. Okay, so this is the standard procedure. This is renormalizing a quantum field theory in an external background. Okay, you apply exactly the same technology that you do when you renormalize a theory. You analyze counter term, you power count. The only thing is that, given that you have a background, you have more structures that you can create that can be associated with divergences. You also can have divergences that are purely function of your external background. Okay, you can form divergences with your fields, but also dynamical fields, but also with your external background, and you have to normalize all of them in order to have a finite action of the external source and of the couplings. In a sense, this external source is like a generalized coupling. It's like a coupling that depends on position. Okay, so normally you want to make the path integral finite as a function of the couplings, and now you make it finite as a function of this position-dependent coupling. Now, there's one general. This is why quantum field theory is subtle and interesting. Is that even if you have symmetries of your classical theory, when you regulate it, you may have to break them. You may have no other option than breaking them. And this is the whole story around the notion of anomalies. And here there is exactly this issue. And in particular, it is evident, okay? You see, if you want to regulate, you have to formally add a scale, like a cutoff or something, okay? Or change dimension in such a way, let's say, if you add a scale, it's pretty clear, right, that your original scale invariance is broken by the presence of this scale. And break scale invariance, you also break Weil invariance, okay, they're related. So if you had an original Lagrangian at the classical level with the metric was Weil invariant, when you have to regulate it, the introduction of a regulator breaks this symmetry. Okay, this breaking has to do precisely with the regulator. So, like in the case of anomalies, all the effects of the breaking will be associated with local terms in the action. So let me say like this. So you have the variation. So the fact that the regulator is not invariant tells you that the action. So now you have a quantum effective action W, which is purely a function of the metric. Okay. So let me say better perhaps. So you have an action, okay, that ideally at the classical level is Weil invariant. So you rescale the fields, you rescale the metric, suitably it's invariant, but you have to regulate it. When you regulate it, you change your path integral, okay, if you want, and you add additional stuff in such a way that your new action with the new stuff, let's say the regulator, perhaps the Pauli-Villard fields, is not endowed with that symmetry, okay? So in particular, the regulator breaks Weil invariance. And therefore, the quantum effective action that you get from this procedure will not be invariant, okay? However, if the breaking has only to do with the regulator, okay, is genuinely associated with the regulator, and in this case, you can see it very nicely when you do dimension regularization, then, I mean, then the variation of the action is local, okay? On the other hand, if you truly, genuinely have an interacting theory which does even which does break the symmetry beyond the regulation, if in an ordinary quantum field theory without conformal invariance, then you would have this to be non-local. Okay, so what you have is that in a CFT instead the variation of the action is local, is what is called the Weil anomaly. Okay, and if you want, if these were non-local, okay, you understand it very well. If these were non-local, the variation of the action with respect to sigma here, it amounts to an insertion of the trace of the energy momentum tensor. Okay, so the variation with respect to g mu nu times g mu mu is an insertion of t mu mu. Okay, if this is non-local, it means that correlator of t mu mu are non-zero, non-locally far away. Okay, which means that t mu mu is really a non-trivial operator, which means the theory is not conformal invariant. The only possible subtlety can arise when the t mu mu's are all at the same point. Okay, in that case, however, the lack of symmetry is encoded by a local term, and this is what is known as an anomaly. Okay, so normally, okay, take this as a result. Okay, that if the theory is conformal invariant when you regulate it, the partition function, the quantum effective action, is symmetric up to a local anomaly. Okay, and that was discovered by Christensen in the case of Weil symmetry by Christensen and Duff in 1974. The same month, as nicely explained in a memoir by Duff, the same month at the same conference when Hawking announced his evaporation of black holes, and so everybody forgot about the Weil anomaly. Only that then, as Duff says, 2 years later, in some contest, black hole evaporation was interpreted in terms of the Weil anomaly. So the two things had shown to be related in some circumstances that now I forgot. So let's now consider the structure of this Weil anomaly. So the Weil anomaly is the variation of the quantum effective action of a conformal theory under Weil transformations. So it is, the Weyl anomaly has the property, like all anomalies, to be the derivative of something. It is the derivative of a certain functional with respect sorry? Not yet. Not yet, sorry. Not yet. You're right. Sorry, thank you. I'm only adding the metric at this moment. Okay. If the theory had not been conformal, then I would have to compensate changing the couplings. You're right. If the theory is conformal, I can keep the coupling frozen. Okay. Yes. Thank you. Not yet doing that. In fact, I'll do that probably much later. Perhaps I won't even do it now that I realize, because the whole discussion about that would have taken. Yeah, this was an old presentation, and now I'll cut it to the bare bone. Okay. Thank you. Anyway, so the Weyl anomaly is a derivative. Okay, is a derivative in a certain direction in field space of the action, of the quantum effective action. So by the way, all the statement that I made here about the locality of the anomaly, I mean the locality of the variation, you can check it in nicely if you really want to really see things in dimensional regularization in a bunch of situations. And there is in a paper I wrote about a year ago, there's an appendix where this is discussed in detail. Okay, so if anyone is interested, you can go and look into that appendix. That appendix is building on very nice work done by Hugh Osborne, Jack and Osborne himself alone in the early 90s. Okay, and this is beautiful work which involves a lot of computation, because it was studying the structure of the anomaly even in a theory which is non-conformal, okay, introducing external sources, as I was saying, and then becomes a tour de force in computations to really control the structure. And but it turns out to be essential to pin down all the results I'm going to discuss this afternoon in a more rigorous way. Okay. So the structure of the Weyl anomaly. So the Weyl anomaly is a derivative. So as you know, when you have a quantity that is a derivative, it should satisfy consistency condition. So if you have a vector vi, and you know that this vector is the derivative of a scalar, then you know that the vector should satisfy dj vi minus di vj equals 0. Must satisfy some integrability condition. Okay, if you know the vector is itself a derivative, it must you know for sure that it must satisfy this equation. It's an integrability condition. It's a consistency condition. The same thing for the anomaly. Okay. I haven't yet gotten to that. This is the next transparency. Sorry, but we'll get to that in a moment. Okay. Now, what is the general form of the anomaly? The general form of the anomaly is just by power counting, is anomalies are associated to divergences, and the only divergences that really matter are logarithmic divergences in quantum field theory, if you want, and logarithmic divergences give you counter terms that have the dimensionality of your space, and in this case the anomaly will have precisely that property. So just by power counting, the most general form of the anomaly is an object that satisfies all the possible symmetries, that is to say, in this case, diff invariance. Okay. Remember, the anomaly is a functional. Okay. The variation is an integral of something. This is diff invariant. Sigma is a diff scalar. So therefore, this quantity here must be diff invariant. A must be diff invariant. So it must be a linear combination of objects of dimension 4, the most general combination of dimension 4 objects that you can form. And here they are. There is the Euler density, which is this combination. You can write them in this way. You can choose whatever basis you want. The Euler density is a combination of powers of the curvature, the Weyl tensor, the richest scalar square, and the total derivative. Now, it turns out that when you have an anomaly, the anomaly has some trivial parts, and the trivial parts are associated with those terms that you can write themselves as the variation of another local term. Okay? So if you look at this, well, in fact, there are also other two terms that I have not added, which are not related to logs, but they're just related to power divergence, so that you could add. But in fact, you see they're trivial. They're trivial because you can get rid of them by adding a suitable local counter term to your action. A local counter term of this form has a variation, which is precisely the form of this plus that plus that. So you can get rid of these guys just by suitably adding your counter terms. Okay? If you want, I can say something more general. The general form of the anomaly, if you want, involves all possible divergences that you can get in the theory, okay, when you send the cutoff to infinity. And the divergences have dimension 4, 2, and 0, okay, just ordinary power counting. Of course, the interesting ones are the logarithmic divergences, but you can also have something related to power divergences when you regulate the theory. Luckily, the power divergences, which truly depend on the cutoff, are associated to the variation of local counterterms, so you can really get rid of them. So all that is left that cannot be eliminated by the suitable addition of local counterterm are these three terms. Okay, the Euler density, the Ricci square, and the Weil tensor square. Now we come to what I was saying before. An anomaly is a derivative of a functional. Okay, so it must satisfy an integrability condition. In field theory, the integrability condition that I wrote here is known as West-Zumino consistency condition. So it tells you that if I take, so as you know, precisely like in this case, if I do, so this is equal to di dj minus dj di alpha, and that's equal to 0. Okay, these two guys commute, and the Weil transformation represent an abelian group, so no matter in what order you do a Weil transformation, the result is the same. Very much like here, his translation in a sort of Euclidean space. Translations commute, so this is, you do first in dj and 4 in di, and vice versa, you get the same result. That's one way to see it, and that generalizes to this in the case of functionals. So you know that the anomaly is a derivative of some functional. See here, W is playing the role of alpha. So you know that this has to be 0, very much like in this case. And that gives you a condition on a consistency condition on the structure of the anomaly. And what you find by imposing this consistency condition is that this term is not consistent. Okay? So this term is not consistent, and this term cannot arise as the variation of a functional. Okay, it cannot. Okay, a local term like that cannot arise as a Weil variation of a functional. So at the end, the anomaly of a conformal field theory is associated in the external metric. It's just given by two terms, called A and C. One is the coefficient of the Euler term. It's a topological density. Okay, this is the Euler density that tells you the topology of the manifold. It's a total derivative locally, okay? So you integrate it over a manifold, it gives you information about its topology. It's the Euler characteristic. And this instead is the Weil tensor, which is a tensor that multiplied by square root of g is Weil invariant itself. Okay, so you can check all the things I've said by using these results, okay? They're using the transformation property of all the Lego pieces of the actions I wrote before. Okay? Just as an exercise if you want. Now, these A and C, which arise in all cases, the anomaly coefficients are physical quantities, okay? Very much like for the chiral anomaly, the anomaly coefficient is describing the correlator of three currents, okay? The triangle correlator of three currents. In the case of the Weil symmetry, the anomaly coefficients describe the 2 and the 3-point function of the energy momentum tensor. Okay, particularly the C coefficient describes the 2-point function, the correlator of two energy momentum tensors, and the A describes a certain tensor structure in the correlator of three energy momentum tensors. And you may want to know, it may be interesting to know what these A and C are in the theories that we know best and that we use most, that is to say, free field theory. And they have this form. And if you see, they basically count the number of degrees of freedom, scalars, fermions, and vectors, a given weight. So they are a weighted measure of the number of degrees of freedom. It's not just number of scalars plus number of vectors. So you would have thought that a more intuitive measure of the number of degrees of freedom would be the number of scalars plus twice the number of fermions plus of Weyl fermions plus twice the number of vectors, okay, because they have two polarizations. Now, if it's Dirac, you put 4, okay. Instead, in this other perspective, degrees of freedom are counted in a very different way. So, from the point of view of the A anomaly, you see a vector as a value 62, while a scalar has value 1. Okay, so vectors are a lot more valuable from the point of view of the anomaly. And now, it turns out that there was a conjecture made long ago by Cardi, which was stating that this A has a peculiar property, and it is the following. Now, it's intuitive that when you go from the UV to the infrared, the number of degrees of freedom decreases, right? You can see it in the standard model, okay? You go from lots of fields, and then some of them get a mass, you get less, then some other get a mass, you get less, some other get a mass, you get less. It's a bit more complicated to see what happens when you go through a strong interaction phase like QCD. You have gluons and quarks, you go through and you get just in the infrared pions, so you get less, okay? So there is the notion, intrinsic notion, that the number of degrees of freedom decreases monotonically when you go to lower energies, okay? But there's no proof of it, okay? And there's no way to make this rigorous in the case where you have strong dynamics and you don't even know what degrees of freedom are, okay? So this counting here, when you have a strongly coupled theory, you have no idea how to define, okay? This is to define degrees of freedom this way, you really need the theory to be free, okay? You're counting, if you're counting, or if you have a theory that is interacting, okay, and it has some asymptotic states, okay, with mass, then you can count degrees of freedom like this in terms of asymptotic states. So you could count as degrees of freedom below a certain mass in the following way in terms of asymptotic states, in a sense. But a theory that is scale invariant, the conformal invariant, where the S matrix is not even well defined, you wouldn't even do that. So what is the right notion of number of, so we still have this, we would think that there is an intuitive notion of degrees of freedom that decreases along the flow. And it turns out that, so now in 1988, Cardi made a conjecture that A is such a quantity. That A is, now here A in general, okay, not just in the closed free field case, but in general A is a quantity that monotonically decreases along the RG flow, okay? So this is Cardi's conjecture on the monotonical decrease of A towards the infrared. I mean, Cardi is 88, made this conjecture based on some evidence, but also based on a result that was derived 2 years previously by Zamolodchikov in 86, and then refined in 87 by Polchinski, that in 2 dimensions there is a similar, the proof of a similar statement in 2 dimensions. In that case, the coefficient that decreases monotonically is C. C is the coefficient of the unique Weyl anomaly you have in 2 dimensions. In 2 dimensions, the Weyl anomaly consists of just one term, C, and it's precisely the term that controls the 2-point function energy momentum tensor. And using this simple 2-point function property of C, C is a 2-point function of T, people could prove, in particular Zamolodchikov, that C is a quantity that monotonically decreases along the energy flow. Okay. In particular, notice that R in two dimension plays the role of the Euler density in two dimension. So in two dimension, what we call C is more closely related to what we call A in four dimension, is the coefficient of the topological term in the Weyl anomaly, the Euler term. So the proof, so Cardy's A theorem was conjecture. Cardy's conjecture was put forward in 1988, and evidence was accumulated in the course of the following 2 decades. In particular, in the case of supersymmetric gauge theories, with the use of Seiberg duality and other results, one could check on a case-by-case basis that the A conjecture of Cardy was satisfied. Okay, it was always satisfied. But in spite of many attempts, a proof was missing. Osborne, in his approaches of the early 90s, had gotten pretty close to, in fact, he did prove it in a sense, the theorem at the perturbative level, okay? But a full non-perturbative proof was missing, but this proof was given, finally came in 2011, and the methodology with which the proof was given has opened the door for more investigations, okay? So the last 2-3 years have been interesting for this problem. So let me give you the proof of the A theorem. So first I have to give you the assumptions. Okay. So the assumption is the following. So the assumption is the following. I have a theory. Okay, here I have a simplified way of saying things. So I have a theory that in the far UV at very, very high energy flows to some conformal theory LUV. Let's assume you have a theory in UV, far UV asymptotes to a given conformal theory. So all the correlators in the very, very, very high energy regime are well understood in terms of the correlators of a conformal theory, which may even be strongly coupled, doesn't necessarily have to be weakly coupled or free. Okay. Then this theory possesses some class of relevant operators, operator of dimension less or equal than less than 4. Okay, and let's assume these deformations, these relevant deformations are turned on. Only the relevant ones. I'm not turning on the irrelevant one, because if I turn on the relevant ones, the relevant deformation will grow in the UV, and at a certain point they will become strong, and I will not know what I'm doing. Okay, I don't want here. I'm not taking an effective field theory perspective. I'm considering an idealized situation where I only have the relevant ones. Is the analog of a normalizable theory. Okay, I want to have a situation where I can really send the cutoff of the theory to infinity. It's an idealized situation in order to derive, if you want, rigorous results. Very much like those you derive when you consider renormalizable theories. Okay, and then it's up to us to apply these results to concrete realistic situation where we do have these high dimensional operators, but that's another story. Okay, so let's assume you have these relevant guys turned on, and for the sake of simplicity, I will assume they're all controlled by one scale, M, which is the analog of QCD scale. Okay, is the scale where the new where this deformation will become order 1. So as I said, these couplings, we have couplings lambda I. They go like M to the DI, okay? And lambda I bar, roughly, of E, go like M over E to the DI. So this is just, in the language of the previous lectures, or the first lectures, these are couplings that grow in the infrared. When the couplings become of order 1, they are a big perturbation. You are order 1 away from the fixed point. This is where you are, okay? When you come down, something happens, God knows what, okay? And the theory reemerges at lower energies in a new form, okay? And asymptotes a new fixed point, my IR fixed point, and in this when you go to energies way below M, it means the fact that the theory is asymptotic at fixed point means that the Lagrangian that emerges below is the fixed point Lagrangian plus only irrelevant operators. Okay, so from that point on, all the terms I have are irrelevant. That's the assumption. The assumption that if a theory is flowing towards a fixed point, it means that only irrelevant operators are turned on. Because if relevant one will be turned on, at a certain point I will go away, okay? The relevant one drive you away from a fixed point. So the very assumption that I'm flowing toward this fixed point tells me that in this situation there are only the irrelevant ones, okay? So operators are suppressed by positive powers of the mass. So their effect, so this is what happens above, okay? And below, there's a new set of couplings by index A, lambda A, go like M to the minus dA, where D, D are always positive here, okay? Meaning that here are relevant, and here they are irrelevant. Okay? And so the effective coupling lambda A bar is simply given by E minus M to the dA, and they go to 0 towards the infrared, okay? So now this could happen because we tuned very cleverly these guys here in such a way that in this theory, the relevant guys are not turned on. That's a possibility we tuned. Or simply because in this theory, emergent theory here, there are no relevant operators, okay? Just the new fixed point does not have any relevant operators, so could be free field theory, like for instance, QED with only a photon does not have any relevant operators, okay? It flows necessarily to a free fixed point. So there are examples of that. Now consider putting this system in an external metric, okay? Consider now taking this system and turn on an external metric, okay? And so we have to try to make sense of the theory in external metric. So we have to crank in the usual methodology of renormalization, okay? In order to make sense of the whole quantum effective action, we will have to add counter terms which involve purely the metric in such a way. In fact, perhaps even counter terms involve the metric and other operators of the Lagrangian, okay? In such a way that the quantum effective action is finite. So in particular, if this Lagrangian here originally was defined without curvature terms, in general, we will need to add terms which involve curvature, like R phi square may be needed to be added in order to make the quantum effective action finite. Okay, you have to cancel all divergences. And of course, the understanding is that you have to add only the counter terms have dimension less or equal than 4. Okay, and what describes the dimension in the scaling? Remember, this theory is going to a fixed point, so there's a well-defined notion of dimensionality in the power counting, because the theory is flowing to fixed points, so we know what the dimension of operators are. Okay, so we can do power counting. Then this theory, the theory is so defined. This is the fundamental Lagrangian, if you want, and then the theory will flow to a new. Will cross, and then we'll go to the new fixed point in the infrared. And now the theory in the infrared, as I said, is this. Sorry, I should say there's something I not emphasized well. Okay, I should say it well. So the theory is, I should give you a drawing here. Okay, I should draw something here. So I should make a drawing. So there is the UV theory characterized by LUV. Okay, then it flows, and this is IR, and there is LIR. Okay, so the theory is described by a certain Lagrangian, effective Lagrangian associated with a fixed point in the UV. Okay, for instance, quarks and gluons. Okay, just an example. The QCD theory flows in the far UV to a free theory of quarks and gluons. Flows, and in the IR is, let's say, massless QCD, and the IR is described by a free theory of pions. Okay, say massless QCD. Okay, and if you want, in this case, this is the Lagrangian of quarks and gluons. This m to the di is one way to say that the gauge coupling grows towards the infrared, so it's relevant. although the growth is not power-like, it's logarithmic, but that's another story. Okay, this is just details. And this L here is, you should interpret this as the effective Lagrangian of the infrared fixed point, okay, describing the pions, okay. You can consistently describe the infrared physics in terms of this effective Lagrangian for the pions or whatever. This pion quarks gluons analogy is just I'm giving to you to give you something concrete to think of, but we're thinking in general, okay. There is some theory in the UV and some effective description in the infrared, and they are both conformal invariant and different, okay. You start from the UV, you are conformal invariant, something happens at scale m, big war, and then you go back to a new fixed point, okay. Now I'm describing this in an external metric, so I have my UV theory, the operators that describe in a simple way UV physics that have definite dimension under the conformal transformation of the UV theory, and this all flies in the IR in a new effective description, perhaps pions, and effective operators in terms of pions. And of course, you also have additional terms involving the metric. Now this, you can think of this as an effective Lagrangian. Here you will have all possible terms that involve the metric and the scale m, okay? So you will have particular, for instance, you can have here corrections to the cosmological constant that go like m to the fourth, okay? That come from quantum fluctuation of scale m to the fourth. There may have been a original cosmological constant here that you counter-terminate with a suitable counter-term. But if you cancel the cosmological constant here, the lambda to the fourth term is not guaranteed that you will not have a term there, okay? Just a normalization, okay? And then you can have terms which involve 1 power of Ricci, m square, and so on. So you have all possible local terms involving m, above or below. While here you have all possible counter terms. Here you can interpret this as the counter terms that you can add. So these are only terms of positive dimension up to 4. Okay. So these are all the counter terms that you can add. And so to tell you the story, if you only look at operator of dimension less or equal than 4, the structure of these two delta that you have to add involving the metric is the same. Okay. The structure of these two Lagrangians is the same, okay? Only that this one here will also involve all higher dimensional terms, all suppressed by powers of m. But the higher dimensional terms suppressed by powers of m, at the very far infrared, they are negligible, so we neglect them. But if you only look at the terms that are relevant or marginal, which have either positive dimension of mass as a coefficient, they are the same, they're the same structure. So let me now make a specific further simplification. Let me now consider the case where the metric is conformally flat. I just take a very specific background, okay, the conformally flat background, which is also called the dilaton background. And now I can power count all the terms in delta L that I can write down, okay? Let me power count all the possible terms. So this analysis is really important for what I have to say, okay? So let me tell you why I'm doing it. What I'm doing this because I want to show in the end that I can compute certain correlators for this external dilaton field that do not depend at all on the regularization, okay? They only depend on the anomaly. And let me tell you how it goes. So these are so when I put a theory in an external field, I normally have to regulate. So there are new divergences that appear, and which means that I need to introduce new couplings, okay? So in particular, if there is operators, for instance, of dimension 2, let's say, I will have logarithmic divergences of the type R times O, okay? For instance, if I have a scalar, I can have logarithmic divergences R phi square, okay? So in order to make the Lagrangian finite, I have introduced a new coupling. The theory with the external metric has a new coupling that the theory without the external metric does not have. Okay, it contains more stuff, and this more stuff, it's up to me to decide what it is. This is not good, okay? I would like to have a situation where there's no extra stuff, and then I'm only testing the parameters of the original theory. So if I have an operator of dimension less than or equal than 2, I will have operator of dimension less than 4. This is dimension 2. This is dimension less than 2, so this dimension 4. It can appear as a counter term. I could also imagine objects like this, okay? But in sensible theories, these guys have all dimensions bigger than 4, okay? If I put here a current, it's hard to make currents that have dimension less than 2, okay? For instance, d mu phi d mu phi is a current as dimension 2, d mu and phi is a scalar. So 2, 2, 1, 5, this is dimension 5, is irrelevant. Same thing here, you have to find currents which have the two indices have dimension 2 to make this dimension 4. But again, the smallest dimension is d mu, d nu phi, and everything else is dimension more than 3. So close to, this is for the case of free theories. You can prove this is the case also in conformal theories. In conformal theories, it's exactly the same, okay? You cannot, the lowest dimension current, J mu, which is not a primary field, has dimension 2. If this were a primary field, this would have dimension at least 3. And if this were a primary dimension 2 symmetric tensor, the symmetric tensor would have dimension at least 4. So these are just results in conformal theory. So in general, you can say that these terms are not important. And then there are terms that purely involve the metric. There's a cosmological constant, there's a Ricci scalar, there's a Ricci square, there is themselves terms like this that you can add as counter term. Now, if you consider a specific case of a metric which is proportional to omega, g mu nu is omega square eta mu nu, what happens is that this term vanishes because this term is the Weil tensor. The Weil tensor does not depend on the overall local scale of the metric. It's Weil invariant by construction, this term. So this term would be 0 if you have a conformally flat metric. This term is 0 if the topology is trivial, but anyway, this is topological. It doesn't give you any local effects, okay? So this is always irrelevant. But let's think that we are working on flat space, asymptotical, so it's the total derivative, it's 0. And all that is left is a cosmological constant term and terms proportional to box omega. So now, if you further assume, so in general you will have divergences associated with this, and this term. Particular logarithmic divergence associated with that require the introduction of a new parameter. However, if you constrain yourself to configurations that are on shell, and here on shell only means box omega equals 0, okay? That's all there is, okay? There's nothing deep. A configuration which has box omega equals 0, then also all these other terms go away. And all is left is a cosmological constant, which is a constant, okay? It's a constant, okay? Omega to the 4th. So if I want to consider the quantum effective action, okay, for this external metric, conformally flat metric, and I further take the metric not for general omega, but on a shell satisfying box omega equals 0, then the quantum effective action, the finite quantum effective action, is controlled by in terms of parameters, by the renormalized parameter of the original quantum field theory plus the cosmological constant and nothing else. There's no more parameter that you need to add. There's no additional renormalization you need to perform. Or on the other hand, if you were off shell, you would need to have the parameter associated with this, for instance, to this counter term. So this is what it means, okay? So now, schematically on this surface satisfying box omega equals 0, the Lagrange, the effective action is already renormalized without adding new without doing further normalization. In other words, the effective action for the external metric is finite, is automatically finite apart from a cosmological constant term. Okay, so from now on, I will consider the following quantity. I will take the quantum effective action, and I'll consider derivatives with respect to omega, okay? And then I can interpret these derivatives in terms of scattering amplitudes, okay? The derivative of the effective action with respect to the external field, okay? I can interpret it as a scattering amplitude. Very much like, let me give you an example. I can consider QCD, okay? And couple QCD to an external photon field. Okay, and now I want to consider scattering amplitude of photons that are mediated purely by QCD. Let me say that I turn off, there's no electron, there's nothing, okay? And I want to consider scattering of photons that is purely induced by QCD. Okay, so what do? I turn on the photon, couple it to QCD, integrate out, compute the quantum effective action, so do the path integral for all the QCD variables, quarks and gluons, and then I obtain a quantum effective action for the photon. The derivatives of this quantum effective action for respect to the photon field on shell, they correspond to QCD mediated and photon amplitudes. In particular, with 4 derivatives, I'll have the light by light scattering from QCD. I'm doing here exactly the same for the dilaton, okay, for the external omega. Notice that this is, if you want, this is a correlator of 4 currents, 4 QED currents made of quarks, okay? So the leading effect of that thing is this guy here, okay? Quarks. But then you also have all the gluons inside it, okay? And now I'm doing the same thing and of course this functional here satisfies some very important symmetry, gauge symmetry, okay? In our case, the role of gauge symmetry is played by conformal invariance and Weyl invariance. So I'm now going to do the same. I'll now consider the analog of QFT, not QCD, my QFT, mediated dilaton by dilaton scattering. Okay, and it turns out that this quantity, dilaton scattering, affords a remarkable insight into the structure of the quantum field theory. So as I said, like for all amplitudes involving dilatons on shell, satisfying box omega equals 0 on shell, the only normalization needed to define this amplitude is the cosmological constant. The amplitude is automatically finite up to a constant term. The constant term is trivial, okay? You can track it down immediately. So here, I don't know how to say it. Let me say it. This is a bit technical. I don't know whether I should insist on this. So this is our dilaton field. You have to be slightly careful that, yeah, roughly the derivative with respect to the dilaton amounts to the insertion of a trace of T mu mu. However, a trace of T mu mu is the variation with respect to the dilaton times G mu mu. So it's actually the derivative with respect to the log of the dilaton. So if you take into account this relation, okay, and the amplitude are the derivative with respect to this, and the energy momentum tensor is the derivative with respect to that, the trace. So when you take 4 insertion of this derivative, you don't get just 4 insertion of T, but you also get cases where 2D, where 1D acts on the 1 over omega of the other. So you also get, in addition to 4 points, you get 3 and 2 point correlators of T. So the true amplitude for 2 to 2 dilaton scattering involves a 4T correlator, a 3T correlator, and a 2T correlator. If you want, you can view it this way. So, and it can be written as ordinary, okay? An amplitude of 4 fields is just controlled up to conservation of momentum by the 2 Mandelstam parameter S and T. So this is a way to express this 3, 4, and 2.4, 3, and 2 point function, okay? There are situations where the dilatons all enter at different points, but there are, given that the dilaton field is nonlinear, there are situations where the 2 dilatons enter at the same T insertion, and situations where 2 dilatons enter at both, and so you have something like that. That's just the diagrammatics of the scattering amplitude. So if you want, this scattering amplitude is a very nice, it's a very nice and very clever combination of 4, 3, and 2 point function of the trace of T. And it turns out to be a combination which has the right properties, okay? Now, it turns out that if you now consider a CFT, if you now this is what I said was basically in general quantum field theory. Now consider a CFT, okay? Imagine you have a theory which is a CFT, that is to say, one of the 2 theories we have either in the UV or in the IR, okay? So what I want to claim is that, so according to what we say, well, as you will see in a moment, the effective action in this case is local and fully determined by the Weyl anomaly, okay, up to a cosmological constant term. Let me tell you the following. So if you neglect the cosmological term that you can always add, which you know it exists, forget it. In the absence of the cosmological term, the Weyl anomaly equation is telling you this, okay? It's telling you that the following. The Weyl anomaly is telling you that if you take the generative function of a CFT, Okay? So if you want, let me say it in a better way. A dilaton background of this type, okay? Dilaton background of this form is related to the trivial background by up to a Weyl transformation. By doing a finite Weyl transformation, you can go from this background to that background. A Weyl transformation is simply rescaling, local rescaling of the metric. By doing a suitable Weyl transformation, you can rescale away omega. Okay? Okay? So, in particular, if the theory were exactly Weyl invariant, omega would drop out. If the effective action were exactly Weyl invariant, omega would drop out of the action. Okay? But the action is Weyl invariant up to the anomaly. And up to the anomaly, okay? And you can also keep the cosmological constant term for fun. It's interesting to keep it. As I said, the cosmological constant, I may set to 0 the cosmological constant term in the UV, but it will not be 0 in the IR, okay? So the cosmological constant term up to that, if the theory were exactly conformally Weyl invariant, then I could get rid of omega. But the theory is not exactly Weyl invariant. It's Weyl invariant up to an anomaly. Okay, and it's a well-known result, which again was first pointed out by my friend Capelli, who is not here today. He came yesterday, but I'm talking about him today. And in '88, okay, and that was done very well. That was done. You're so funny. Okay. No, Andrea, this is why. So I just mentioned that. Unfortunately, you came yesterday just to see your name mentioned, but I did not mention it yesterday, and now today you didn't come. But then, okay. Well, the timing was very good. This is the proof that fine-tuning may exist. Okay, if you want out of all this crap about naturalness and all that, there it is. Okay, but you need special people. You need special people to do that. Chosen by the landscape. Okay, this anthropic selection. So okay, so in these papers, it was computed how the action transforms under, so the infinitesimal transformation is given by the Weyl anomaly. To get the finite transformation, you have to integrate the anomaly, okay? And the integration of the anomaly gives you, so the finite transformation, so when you rescale the metric, you get back the metric without the omega, and a term which is an integral of the anomaly, which is, because interpretation of West-Zumino term is called, okay? And it has the following form. It is proportional to the two anomaly coefficients, okay? And it involves clearly at the leading order when omega is just 1 plus something, where log omega is just a small thing, then you get precisely E4 and W squared, which is the two anomaly terms. But when omega is finite, you get more stuff, okay? And you get stuff involving the metric and omega, and you get stuff involving box omega, and you get a term that looks like a scattering amplitude. Okay, it has 4 omega, and for derivatives is like a 4 scattering amplitude. And now we simply have to compute. Now we're interested in the case where G mu nu is the trivial metric. So this, and this drop, and all we're left with is this. And by the way, this term here is the action of the conformal Galilean for whoever is doing cosmology. So I had also derived this many years after Andrea, actually in 2008, 20 years after Andrea, without knowing that he had already done it. Although we talk from time to time, but he never told me that. There's nothing special, yeah, but it's one of my most important results. So it's not special for you, for me it's very important. For you, I see the hierarchy of okay. Okay, so the net result is that in the CFT, if you allow the fact that there is a cosmological constant term, which would always subtract, okay, as I told you in the beginning, the cosmological constant term can always be added and subtracted to the action. However, if I add a counter term in such a way that this term is absent in the UV theory, when I expand the dilaton action in the UV, in the far UV, if I choose the counter in such a way that this is not there in the UV, I'm not guaranteed that this is not there in the IR. There will be some contribution coming from M. Okay. Remember here I'm looking at the properties of the UV or the IR theory. And so the quantum, the effective action for the dilaton is dominated by A, okay, by the anomaly, it's just controlled by the anomaly, and plus this boring cosmological constant term that you will see beautifully disappears, okay, in a moment, okay. I keep it just to show that the result is robust, that there is no subtlety concerning this term. People were confused in the beginning about this, okay. And so the net result is that the scattering amplitude of the dilaton is simply given by a four derivative action, so it has this property, S squared plus, it has this, just do a computation, it's a trivial Feynman diagram, plus the cosmological constant term. Cosmological constant term, you know, the metric square root of G is omega to the fourth. Say, if the metric is this, square root of G is just omega to the fourth, okay? So, cosmological constant term just is like a phi to the fourth interaction. And this basic result is all we need to prove the A theorem, okay? And the A theorem is proven starting from this result applying dispersion relations. And I believe it's better if I do that later, or I can finish now. Because people are probably tired, or I can do it in 5 minutes. I can do it in 5 minutes. So we have this amplitude. So this is the amplitude that the dilaton amplitude, the background dilaton amplitude is in an exact CFT. Now, we don't have an exact CFT. We have a certain CFT in the UV, we have a certain CFT in the IR. Okay? So if you compute the dilaton scattering at very, very high energy, we expect to be getting this formula for the parameters of the UV theory. And if we do dilaton scattering at very, very, very low energy, very, 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 very low, we'll get the same result where A and lambda are those of the IR theory. Okay? That's just effective field theory. Okay? And now, these two different results are different, okay, and but they are related by the same. They are in the same theory. They are the IR image of something else. This is very similar. What I'm going to do now is very much the same as when you have light traveling in a medium. You have light traveling in a medium, and you can ask yourself, what is the speed of light at very, very, very large frequencies? What is the speed of light at very large frequencies in a medium? Does anyone know? No, with first digit, okay, without 5 digits. The same to what? The same as C, what is 1. Okay, it's 1. Okay, it's 1. What is the speed of light in the medium like water at wavelengths longer than the atomic size? Or of the order of even longer? Well, we don't know, okay. But is it 1 or 2? Is it 2? How do you know it's not 2? How do you know it's not 2? How can you prove me it's not 2? Why? I mean, dispersion relations, Kramers-Kronig, Jackson, go read it. Okay, so, and this is going to be exactly the same. Very much like in a medium, you can prove that the speed of light at frequencies that are much longer than whatever frequency you can have. If you assume that C is 1 in the far UV, which is the assumption that the far UV light doesn't see atom, boom, goes through, then you can prove that, using causality if you want, that the speed of using the property of analyticity of the evolution kernel, if you want, the Green's function, that applying this dispersion relation, and if you want the optical theorem, the fact that absorption exists and gives you a positive effect, you can prove that the speed of light in the far infrared is less than 1, cannot be bigger than 1. Okay, and now the story here is exactly the same. It's exactly the same. Here you prove, applying the generalized dispersion relation, okay, that A in the IR is less than A in the UV. The proof is exactly the same. So let me just sketch it, okay? So let me tell you the story. So you have the UV theory here, I already said it, and the IR theory. So these two theories will imply a certain result for the dilaton scattering amplitude. Let me consider the forward scattering amplitude, which is precisely what you do even when you do the speed of light. You just forward propagation, okay? If you want the imaginary part of the refraction index associated with the total absorption, okay? That's a similar thing. You just consider the forward scattering amplitude, okay? Whose imaginary part by the optical theorem is given by the total corresponds to the total cross section. Let's look at the forward amplitude. So the forward amplitude in the UV and the IR has the following form. In the UV, it is controlled. Let's say it again, okay? If I go forward, I set t to 0, okay? T0, T0, 2 square here, so it's 4, minus 8a, okay? So you get minus 8a, 1 plus terms that vanish as positive powers of m. M is my deformation. All the effects, this deformation is relevant, so the deformation becomes less important in the UV. So all its effect, just by dimensional analysis, will scale like inverse powers of S. Okay, so in the very far UV, you can neglect them. And there's going to be some UVCC. Then there's a similar thing in the IR. You have the IRA, and now when you flow towards the IR, you're flowing towards CFT up to higher dimensional operator. So here, the effects of M appear with the opposite power, okay, plus another CC. And now you can use the properties of the scattering amplitude, and you can relate these two regimes by dispersion relation, okay, by an integral in the complex plane. The scattering amplitude is a consequence of causality. There's a nice discussion of this in one of the last chapters of Weinberg 1. So if you want to know about this, read there, okay, where he studies shows the analyticity of the 2-to-2 scattering amplitude of photons and pions. I think photons and pions. So this amplitude is analytic in the complex S plane with a cut on the real axis. Okay, the cut is on the real axis, and it is crossing invariant. Okay, crossing symmetry here amounts to exchanging at t equals 0 S and U, and because of the relation S plus 3 plus U equals 0, this amounts to exchanging S with minus S. So this is the crossing symmetry. This amplitude can also be proven, like you showed there, to satisfy a reality condition. So if you star it, you get the amplitude at the starred S. And using all these combinations, you have that the difference in the amplitude at the point S plus I epsilon and the point minus S plus I epsilon, 2 points in the upper plane that are that have the same imaginary part but have the minus S. This is equal, if you apply this relation, to the imaginary part of the amplitude, and the imaginary part by the optical theorem is given by the total cross section times S. Okay, total cross section for dilatons absorbed into the QFT. These are background dilatons. Okay. So now you can apply dispersion relation. Dispersion relation just amounts to integrating this amplitude divided by S cube over this contour. And this is a contour in the upper plane, so you can imagine here to be slightly above the real line, okay? So it's all in the upper plane, so it is in the domain of analyticity of this function A of S, so the integral is 0, okay? The integral is 0 just by Cauchy theorem. Now this integral, now imagine taking, however, the limit where this integral consists into 3 well-defined pieces. There's the straight piece and the 2 half circles. And imagine that the 2 half circles, the half circle gives you, so this is the S plane, okay? Imagine the half circle is sufficiently small in S to be contained in the domain of validity of the low energy effective theory. In fact, I can take this small circle as small as I want. I can even shrink it to almost 0, okay? The small circle shrinking to 0 means that we are looking at the amplitude in the IR. The big circle going to infinity, it means that we are looking at here, the amplitude here is the amplitude in the UV. So these 2 circles probe the theory in the IR and the theory in the UV, okay? While this thing here probes the RG flow, okay? So here we have a relation between the IR, and now it's related by the RG flow. Okay, and the sum of these three contributions, IR, UV, and RG, must give 0 because by Cauchy theorem. Now it's a little exercise a trivial exercise in integrals. Okay, to check that the IR integral, it goes this way, is exactly equal to 4 times A. In particular, the cosmological constant term drops out. Okay, the cosmological, this is the integral of ds over s cubed of A. Okay, and if I take a constant piece, okay, ds over s cubed of the cosmological constant term, it's a constant, over the half circle, this is 0. Okay, this is the integral, if you want, of I d theta, 1 over e to the 2I theta, okay, integrated for theta going from 0 to pi, okay. So this is the integral between 0 and pi of I, well, okay, forget the I, d theta e to the minus 2I theta. Okay, so it's the integral between 0 and 2 pi of d theta e to the I theta. So it's a full circle. Okay, the fact that there is a square here, the fact that there is a cube is leaving you some square, and the cosmological constant drops. So both in the UV and the IR. So in the UV, you go the other way around the circle, so you get minus. Okay, and along this trajectory, you get the integral, you get this integral and that integral, and if you use this relation, that this guy is related to that is one equal to the other minus the other by crossing, then these two pieces add together to give you the integral of the imaginary part, and the integral of the imaginary part is the integral of the cross section, which is a positive quantity. This is where unitarity enters. If a theory is unitary, cross sections are positive, okay, or the imaginary parts or forward amplitudes are positive. So this integral is positive. This is where absorption enters. This is the analog of the absorption in the story of the speed of light. Okay, things get absorbed. So the 2 dilaton state has a finite probability of absorption by the CFT, of conversion into the states of the CFT, of the QFT. And because of that, this integral is positive. And now you put everything together, you have that this equation here is tell you that IIR is equal to AUV minus a positive integral. So you have the proof of the A theorem. It's just a trivial dispersion relation. Okay, I will discuss this after lunch. Thank you.
Questions? So here you showed the here you showed like a weaker version of the conjecture. Know that AUV is bigger than AIR.
Why a weaker version? Which conjecture?
So, because you didn't show that the flow is monotonic. No.
If I define it, if the flow, if I define the A at finite scales as the integral over this thing here, a bigger thing, then it's again monotonic. It's a question of definition. It's a question of definition. I mean, the question is what you see. There's a quantity, which is this integral around here. Okay, no matter what it means, it's a quantity which is physical. Of course, it's physical because, well, it's an integral in the complex plane, but it can be with sufficient precision. It can be turned into. I don't have a direct way of associating it to measurable quantities, but it can. Okay, using analyticity. Okay, so that integral is that integral has a positive derivative. So and that's an integral that in the perturbative domain corresponds to A, and when the thing is strongly coupled. Talking about the running of alpha S at the crossing of between the QCD and the pion scale is an irrelevant statement. So in the domain where the running is quick, which is close to the scale M, I mean, what definition do you want? And in the tails, this corresponds to A, and then it works. A twiddle, actually, the quantity A twiddle. If you want, we can discuss. But yeah. So in the end, there is also there's a more. This is not the interesting question. The interesting question is the one that we discussed this afternoon. Is what can we say about the asymptotics of flows? And this is what I discuss here. So if you want this thing about the weak and the strong version, I think it's. I don't know. I don't see the point.
Any other question? Okay, so we thank Riccardo again.